Lesson 3 of 4 for Unit 2 is on average rate of change and the concept of the derivative. We're not going to use the word derivative except for right here. I'm going to kind of introduce you to the concept of it. First thing we need to know is what the slope of a line is. You guys are pretty comfortable with slopes, hopefully. You're used to the equation like y2 minus y1 over x2 minus x1, given a point x, y, and xy. But we're kind of going to move towards inputs and function values. So instead of xy, we're talking about some a and the function value with a plugged in, and b, function value with b plugged in. So we get this slope equation. F of b minus f of a over b minus a. Of course, we should know that if we're rising from left to right, we call this slope as positive. If we have a situation where we are going down from left to right, slope is negative. And if we have a situation where we are flat, what is that slope? Slope is 0. And a slope that is straight up and straight down would be undefined. Okay, just be comfortable with that. Okay, positive goes up, negative goes down, 0 is flat, undefined is vertical. Average rate of change of a function given an interval. These being x values, of course. An average rate of change would be the change in your function. Delta is Greek for change, mathematical symbol for change. Change in your function divided by the change in your interval. Well, what's that the same as? Yeah, it's the same as the slope. Okay, this is really equal to that slope equation that I was talking to. This would represent the change in my function, and this would be the change in my interval. So if I look at a function, some random function, maybe it looks like this. Gosh, I can't do that normally. That was impressive. And I'm looking at the average rate of change of this function between a and b. Well, all I need to do is kind of create a line from a to b. And if I find the slope of that line, that would represent the average rate of change of my function over that interval. Now, when we're talking about average rate of change of things, and we're talking about functions and changes of functions, it's a little bit easier to think of things in the real world. So we can talk about changes of actual things. And this is where calculus and physics go hand in hand. So we'll be dealing with a lot of physics concepts in calculus, because we'll be dealing with changes of things, average rates of changes, and more specifically, we'll be dealing with instantaneous rates of changes of things in this class. It'll be okay. Don't worry. We know position is in meters, velocity is in typically meters per second, and acceleration is meters per second squared. Position is just a location. It's not distance. It's where you are at a certain point. Typically, you think about a number line, and you think about a dude for a car. And you say, this dude at the 2-second mark is at position 5. And then by the 10-second mark, he makes it to position 0. You don't know what happens in between there, but we know he gets there if we're given a table of values. Now, velocity is the change in your position over the change in your time. Or it's the slope of position, the average rate of change of position. And position, we usually use the x of t as the kind of equation we use, t being time, your input, x of t being your position, given your t is time. Velocity, we typically use v of t. Acceleration would be the change in your velocity over your change in time. And this would be, of course, the average rate of change of your velocity, because it's really just slope. So I consider that slope of v of t. And acceleration, we usually use a of t. Okay? So these are all related. To get velocity, you look at position over time. To get acceleration, you look at velocity over time. They're all kind of slopes of one another. Velocity really is the slope or the average rate of change of position. Acceleration is the average rate of change of velocity. Of course, we know velocity can be positive or negative. Positive would be this dude going in the direction to the right. Negative velocity would be this dude going to the left. Okay. Let's talk about the average rate of change of a function. We're given functions modeling the position of an object. We're trying to find, let's move to this one that's similar. We'll come back to that. Okay. We're going to give a table of positions of an object. We're trying to find the average rate of change of the object between 10 seconds and 25 seconds. We'll try to explain what that answer means. So if I want to find the average rate of change of the object and the position of the object between 10 and 25 seconds, what do I do?
25 minus 10 over, yeah, 25 minus 10 over 25 minus 10.
Yes, it would actually be the position over the time, so it'd be 25 minus 6 over 25 minus 10, yes. So I kind of confused you. We're going to do the change in your position over the change in your time when we're talking about this interval from 10 to 25. That's how you find the average rate of change. You find the slope. Change in time is 25 minus 10. We get 19 over 15. But what is the average rate of change of position? What does this answer 19 over 15 mean? Velocity. In particular, it's my average velocity between 10 and 25 seconds. And think about it, if you have position in meters and time in seconds, we have meters minus meters, that gives me meters. I have seconds minus seconds, that gives me seconds, meters per second. Okay, so I found the average velocity of whatever this thing that has these positions. Well, I can do the same thing, given a function, can find the average velocity of a function whose position is modeled by some equation. And this is easy. If I want to find the average velocity given this position, I just take my change in my position divided by my change in time over the interval from -2 to 2. So I need to find my position at -2. That's 8 minus 16. That's -8. And I find my position at 2. That's 8. Sorry, I made a mistake. This is 8 plus 16. This is 24. This is 8 minus 16. This is -8. So once I found those values, I literally just plug into my slope equation, x of b minus x of a over b minus a. And I get -8 minus 24 over 2 plus 2. That's -32 over 4. That is -8. -8 what? Well, if this is in meters, this position, this would be meters per second, if we're talking about t being time in seconds. All right, you guys find the average rate of change of that position from 0 to pi over 2, those being seconds, and that would be the same as finding your average velocity. So it's sine of t from 0 to pi over 2. Check your answer with the neighbor. Make sure you have your y values over your x values. I get 2 over pi because it's 1 over pi over 2. Make sure you keep things in order. Make sure if you have pi over 2 first, you put 1 first. Make sure if you put 0 second, you put the other 0 second. Ms. Wheatley? Okay. Okay, 2 over pi. Good. Average rate of change of a function is just finding the slope between 2 points of the function. That would be the average rate of change. Okay. Now, given a table of positions at certain times. So write down that table. We got 0, 5, 10, 15, 20, 25 for time, position, I have 2, 6, 20, 25, 15, 10. So 0 to 25 by 5s from time. And then for position, I get 2, 6, 20, 25, 15, and 10. The question is, can I find the exact velocity of this dude at the 10-second mark when t equals 10 seconds? So that means if this dude was a car and he starts driving, what does the speedometer read exactly when his stopwatch hits 20 seconds? 10 seconds. This is 10. Now let's think about what I'm given with position. If I start at the 0-second mark, I have a dude at position 2. After 5 seconds, don't hide, I'm going to be at position 6. After 10 seconds, I know I will be at position 20. Lost a part of his body. After 15 seconds, oh, I thought I grouped these. I guess if I keep clicking on it. After 15 seconds, he's going to be at 25. After 20 seconds, he's going to be at 15. And after 25 seconds, he's going to be at 10. However, do we know exactly how this guy moves to all of these positions? No. Between this 0-second and this 5th second, going from 2 to 6, he might sprint all the way down and then come back and stop at 6. You don't know that. All you know that is at time 0, he's at the 2nd position. And at time 5, after 5 seconds, he's going to be at position number 6. Position is not distance, it's where you're located. You don't know if he goes there slowly and just stops there right there. You don't know if he gets to 6 and waits, or goes back and forth a bunch of times and then stops right at those things. Okay? So the question is, can we find the exact velocity of this guy at the 10-second mark when he's located at position 20? No. Not given a table of values. Could we approximate, however, his velocity at the 10-second mark? How? Give me an example. What can I do?
Average rate of change.
I could find the average rate of change of this guy from when to when. What do you think?
5 to 15.
We could try from before he gets to 20 to after he gets to 20. We can think about from 5 to 15. That would be the average rate of change. That would give me the velocity. That would be, let's move this up just so I can see. (25 minus 20) over 15 minus, 25 minus 6, 6. 25 minus 6 over 15 minus 5. That is 19 over 10. That would be meters per second. Sweet. So that would be a decent, but that's kind of a long time frame from 5 to 15 seconds. Could we maybe think of another way we can approximate it? Don't know what distance is. I just know what position is. And what we are doing is distance over time. We are saying he travels from position 25 to position 6. He covered 19 meters in 10 seconds. That's 19 tenths meters per second. Right? So we could do 5 to 15, but maybe we just do from 5 to 10. Maybe we see what he's doing right before he gets to 20. So that is another way we could approximate. You can do 20 minus 6 over 10 minus 5, 14 over 5. That would be meters per second. I could also do 10 to 15, another way to approximate this velocity at this time. You kind of look before, you look after, and you look over the course, and you see maybe we'll have a range of possible velocities. So this would be 25 minus 20 over 15 minus 10. 5 over 5, this is 1. So that's distance over time. Change in position represents the distance. It's really not the distance, it's the displacement. Over the change in time gives us velocity. Okay. What would give me a better approximation of the exact velocity at 10 seconds? Exactly. If I had maybe my position at 9 and 11, I can better understand what's going on right at 10. It's a good idea. What would be better than that? Beautiful. We could think about my position at time 9.99999 and 10.0001, and looking at the average rate of change between those two values would essentially almost be like giving me the exact velocity right at 10 seconds. Okay? So here's the position. It turns out this is how my dude moved. It actually wasn't as crazy as I thought. He kind of moved slowly from 0.2 to 5.6 to 10.20. He kind of went above, and then he came back to 25, then he came back down, and came back to 25. And we said if we wanted to approximate my velocity at this 10-second mark, we took and found a bunch of slopes, right? Between this point 5 and 10, we did from 10 and 15, and we did from 5 to 15, all representing average velocities. Well, Ms. Coffey said, you want to get a better approximation? Look at 9.999 seconds, look at 10.0001 seconds. What would that line look like if I drew a line that is right to the left of this 10 and right to the right of this 10? How would that line look like if I drew that line? I mean, it would be really, really tiny, tiny, but extend it. What would it look like? Like, yeah, almost matching the slope, almost kind of touching this graph at one location, right? It's a tangent line. Wow. All right, intro to tangent lines. Turns out a great approximation would be, and a best would be using points really close to 10. Sorry for saying that so quickly. Okay. Super, super close to 10, like 10.001. Can we get closer than 10.001? Yeah, I can throw some zeros next to that point. So it's really approaching this 10 value from the right and from the left, kind of showing that, boom, get a tangent line. The tangent line is just a line that just nicks your graph at a certain point. Just touches your graph at a point. I'm not going to say it only touches your curve once, because if I look at maybe a tangent line that we would think to be right here, this tangent line, if I continue to extend, would hit it another place. So instead we just say, yes, this is my tangent line at that location, but it's just nicking my graph, just touching it. And it's kind of mimicking, really, it mimics the slope of my curve at the point. And it's not really mimics the slope of my curve at a point, it actually is. So here would be a tangent line right here, kind of mimicking the slope right there. We're talking about 2 points really close. This would be like a tangent line here, tangent line there. This would be a tangent line there. Okay? And if we're talking about the slope of a curve at a point, or we're talking about slope being average rate of change, well, what was average rate of change, which was from one point to another, becomes the slope just at one point, or an instantaneous rate of change. Meaning your velocity at a specific time. Now, first we got to make sure we're comfortable writing equations given lines. We should all be familiar with the point slope form of equation. We should all be familiar that parallel lines have equal slopes. We should all be familiar with perpendicular lines having opposite reciprocal slopes. Great thing, and I won't do all these questions, you'll just review this while you do your homework, is that on calculus tests, if you're asked to write an equation of a line with this slope and this point, you can just leave your answer like that. And you're done. This is the equation of a line. Just because you get y by itself doesn't make it less of an equation or a better equation. Okay, so this would be the equation of this line. And you will have homework problems dealing with lines. Definitely go over those things. Remember, parallel lines equal slopes. Perpendicular lines or normal lines, opposite reciprocal slopes. Okay, but let's go back to these tangent things. Normal and perpendicular are the same, yes. All right, sketch this function really quick. We have 1, 2, 3, 4, 5 points, and we have this function going kind of down, up, and down. Then go ahead and sketch the tangent lines at those 5 points. 1, 2, 3, 4, 5. And make sure your lines are looking like my lines. Just like that. It should make sense. This is like that. There. 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 Now, the slope of this tangent line is what's really important, because the slope of a line is like the average rate of change of something, but we're talking about a tangent line being at one point. We're talking about the instantaneous rate of change of something, the instantaneous change of my function of my point. So I'm worried about the value of this slope. This line right here, what is the slope of this line? Don't be specific, just in general. Negative. Okay, good. This line right here, what is the slope of this line? 0. This guy's positive. This guy's 0. Negative. Well, what I'm going to do is sketch a tangent slope function. Okay, and we have positive y values up here. We have negative y values, but we're going to consider them not y values, but we're going to consider them slopes. These are m values that are positive here or negative here. Well, at 1, I have a negative slope value. At 0, I have a 0 slope value. sorry, at 1, this is at 2. At 1, I have negative. At 2, I have a 0 slope value. At 3, I have a positive slope value. At 4, I have another 0 slope value. At 5, I have a negative slope value. This, that we can kind of connect and smooth out, is our tangent slope function. We call a tangent slope function f with a little line in the exponent, which we call a prime of x. F prime. Okay? This is all of the instantaneous rates of change, or all of the slopes of my tangent lines of this function at any location. Really interesting. We can do that again for a couple more, but I want you guys to look at this. You're cool. If I give you this f, could you tell me which one of these would be the f prime for this f? A, B, or C? Well, I go straight here. I see a 0 tangent slope, a 0 tangent slope. I got 0 here, 0 here. But let's look to the left. This tangent slope is positive. Positive to 0 to negative. So it would be B. Okay? You'll have to do that on your homework. It's not hard. We're going to practice it a lot moving forward. But it's just an introduction to these tangent lines. Yeah, it'll be a little bit more. Wow. All right, let's go back and do the other examples, at least for tangents. So let's say we have a function like this guy. Hold on a second. We can start sketching the tangent lines at these points. What we see is we have a positive slope at 1. We have a less positive slope at 2. A 0 slope at 3. A negative slope, but it's a little less negative than this negative slope down here. Which is interesting. We have a tangent slope function, or this f prime function, to be a straight line. And let's look at this. This is f. This will be my tangent slope function, f prime. At each one of these locations, our tangent slopes will be the same. It'll just be the line. And all of those tangent slopes are all negative. And they're the same value, negative. So like say down here, 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 this would be the f prime equation, the tangent slope equation. Okay, so this is the idea of going from a function to a tangent slope function. We already talked about tangent lines, lines that are just touching graphs at points. We talk about how we can use this tangent line to give us a really great approximation of the change of my position with respect to time, or the average velocity, or really the instantaneous velocity here at the 10th second mark. I'll do these just as quick examples. So if I want to draw or write an equation of a line parallel to y equals negative 3x minus 5 passing through the point 1, 2, well, I know the slope of this equation, since this is a y equals mx plus b equation, is negative 3. So a parallel slope would be the same. I'd go y minus y1. This is the point that my line has to pass through, is equal to that slope times x minus x1. And this is a completely okay equation to leave in calculus class. Now let's think about this one. I want a normal line to this through this 0.15. A normal line is a perpendicular line. So I want something perpendicular to this equation. If I wanted to find the slope of this equation, I'd solve for y. So subtract 3x, divide -7. And I would know that my slope, after I divide by -7, would be 3/7. So I'm going to use the perpendicular slope to be -7/3 in my y minus y1 is equal to m times x minus x1. And this would be my correct equation. And if we have a situation where we have 2 points and we want a normal line that contains these 2 points, it's got to be normal to, we want an equation normal to the line that contains these 2 points, but it's going to have to pass through another point. Let's say, let's go back to 1, 2. So these 2 points make up a line. We have to find the slope of this line. The rise over the run, or the change in the y's over the change in the x's. That's 3/2. Normal to a line with this slope passing through this point would be y minus y1 equals m times x minus x1. Okay, that's it for this lesson. Intro to tangent lines and average rate of change.